This is your exam number 3 review. So if you will look at the top of your notes, it says the graph of a function is shown here. So you see your graph, and we're going to use that graph to find the following. First, we want the intercepts, if there are any, both the x and the y. Well, we know the x-intercepts are where the graph crosses or touches the x-axis. So we have one here and we have one here. So we're just reading them right off of our graph, and that is the point -2, 0 and the point 2, 0. This is -2, 0. This is 2, 0. Let me scoot this over so there's a little bit more to that graph. Now we want to see if there are any y-intercepts where our graph crosses or touches the y-axis, and that would be the point right here. So if you look at that point, is the point 0, 1, 2, 3. So my y-intercept is the point 0, 3. Now we want to know the domain and the range. This is a graph that does not have arrows on the ends of its shape here on either side. It actually has endpoints. So as far as the domain goes, our x values go from -1, 2, 3, 4 all the way over to +4, including -4 and 4. So you can write it like this as an interval, or if you would like to write it as an inequality, it would be -4 is less than or equal to x is less than or equal to 4. Two formats of the same thing. The range is our y values. The lowest the y goes, you notice, is right here. It sits on the x-axis, so we know that is 0. So that interval would be 0 to the highest the y's go is 3. And if we wanted to write that and as an inequality, we would say 0 is less than or equal to y is less than or equal to 3. So either way that you want to write it, interval or as an inequality. C says the intervals on which it is increasing, decreasing, or constant. So I'm going to use some colors here. And let's first do the intervals on which it is increasing. And remember, these are x values. So where is it increasing? It is increasing, let me see how I can do this. It's increasing right here up to here. And then it is increasing right there up to here. So the interval that it is increasing first, it starts increasing when x is -2. It continues up to when x is 0. And then that is in union with, or in conjunction with, along with, however you want to say it. It starts increasing again right after x is 2. Remember, it's not inclusive because at that point it is not increasing. And it continues increasing to x is 4. It looks a little flat here. It really shouldn't. It should kind of go up. The graph isn't quite drawn correctly. I drew it freehanded, and that is why. And speaking of that, let's just look at where it's constant. And it may appear that it is constant here and here. It is not. It's actually increasing up to those points. So there is no constant part of our graph. Where is it decreasing? And I will do that in a different color. It is decreasing on the interval right here down to here, and then it is decreasing again right there. So it starts decreasing when x is -4. It stops decreasing when x is 2 in union with. It starts decreasing again here when x is 0, and it stops decreasing when x is 2. So those are the intervals, the x intervals, where the graph is increasing, decreasing, or constant. Now we have to determine if it is even, odd, or neither, and this one we're really just going to do by inspection. And as you can see, it is actually symmetric across the y-axis. So since it is symmetric to the y-axis, that makes our function even. So it is an even function. Then we want local max and or local min, and we're just going to do those as points rather than the way that I actually showed you in class, because that's a more common way of showing it. So let's first look at our local min This is a local min, this is a local min, so we have a local min at the point -2, 0, and again at the point 2, 0. And now we want to look at a local max. Local max point, this is not, you see these 2 points here are not as high as this one. This is a local max point. This one can't be because the graph doesn't extend to the other side. This one can't be because the graph doesn't extend to the other side. So the only local max point is right here, and that is the point 0, 3. Now it says determine algebraically, and number 2, whether the function is even, odd, or neither. This is not this function, by the way. This is a different function. So up on this one, in example 1, we determined it by inspection. Here we're going to determine it algebraically. And I've told you all along, the first thing you always do is you test negative x. So we're going to find h of negative x. That would be negative x over x squared minus 1. That would be negative x squared. So let me do that in 2 steps. Sorry about that. So it would be negative x. Negative x is x squared minus 1. I got ahead of myself there. And then we compare it. And what do we compare it to? We compare it to this. Is it the same? It is not. So it is not even. Now we check to see if it is odd. So now what we check is negative h of x. So negative h of x would be a negative in front of x over x squared minus 1. I'm going to go ahead and place that negative in front in the numerator. So negative h of x would be negative x over x squared minus 1. Now this time we don't compare to our original, we compare this to what we got when we did h of negative x. And since they are the same, that means that our function is odd. So the first time you compare to the original when you test h of negative x, but when you check negative h of x, you're checking it back against what you got here. That way you can do it in 2 steps actually, rather than 3. Looking at example 3, it says find the average rate of change of f of x equals negative 2x squared plus 4, that's our function, between these points. So we're going to label this A and this B, and in order to determine our average rate of change, which is delta y over delta of x, we have to know what is f of A and f of B. So let's figure f of A here is going to be, I'm going to write this, f of 0, because that's my A, and I'm going to plug that in. Let's scoot over. Sorry about that. Plug that into our function. So f of 0 is equal to negative 2, take out the x, put in a 0, plus 4. Or negative 2 times 0 is just 0, plus 4 is 4. So f of 0 is 4. I'll use that in a minute. And now we want to find f of b, which would be f of 2. So f of 2 is equal to negative 2. Take out the x, put in the 2 squared, which is negative 2 times 4 plus 4. Or f of 2 is equal to negative 4, because it's negative 8 plus 4. So I now have f of 0, which is f of A, and f of 2, which is f of B. So let's remember our formula. Delta y over delta x, which is another way to say slope, is f of B minus f of A over B minus A. Or delta y over delta x is equal to negative 8 over 2. Delta y over delta x is equal to negative 4. So the average rate of change of this function between those 2 points is negative 4. Another way to say that is the slope of the secant line between those 2 points on this function is negative 4. Now let's check it from 1 to 4. So this time this is my A and this is my B. So I need to find f of A, which is f of 1, f of 1 would be negative 2 times 1 squared plus 4, or f of 1 is negative 2 plus 4. My negative didn't show there. F of 1 is a positive 2. So that is my f of A. F of B would be f of 4, because that's my B, and f of 4 is equal to negative 2 times 4 squared plus 4, or f of 4 is negative 2 times 16 plus 4, negative 32 plus 4. F of 4 is equal to negative 28. So I found the parts that I need. So delta y over delta x is equal to f of b minus f of a over b minus a. Delta y over delta x is equal to negative 30 over 3, or delta y over delta x is equal to negative, that's a 3 by the way, not a 5, negative 10, meaning the slope of the secant line for this function between those 2 points is negative 10. It's steeper there, isn't it? This was negative 4, this was negative 10. All right, let's look at our next page. And what we have are graphs that we are going to match, the graphs to their functions. And these are graphs that are written in transformation form, so form 1. So what we have is 6 different functions and 6 different graphs. Now, the easiest way to do this is to find the one that is most like the parent function. So let's stop a second. We know the parent function here is f of x equals x squared. So that would be right there. Okay? So as I look at these, I can see, oh, that looks like f of x could be x squared. But when I look up at my functions, I don't see any. But I see one that has been multiplied by 2, which means it's been narrowed. That must be the closest I can get. So this one is E. Now, you can go through the graphs and match to the function. I actually think it's easier to start with the function and match to the graphs. I just wanted to check first to see if the parent function was there, and this is the closest that we have to the parent function. This one is y squared equals x squared plus 2. So here's my parent function, and then there was a vertical shift up 2. So I'm looking for one that is a parent function moved up 2. So I know that this one is A. So I cross that off. What's another one that is an easy one? This is an easy one because it's a horizontal shift. And it's a negative 2 inside, which means that it was moved to the right 2, but it's the parent function moved to the right 2. So that gives me C for this one, because this one has been moved, its vertex to the right 2. So now I have 3. I've only got 3 left. So I notice that all the rest of them have negatives, and if you notice our graphs, all the rest of them have been flipped across the x-axis. So let's go to this one because it's the simplest of the ones that have negatives, and it shows that skinny, the 2 x squared, but then this has been flipped across. It looks like that is it right there. So now we're down to just 2. So we have a negative x squared and then plus 2, and then we have negative x plus 2 squared. Well, because this plus 2 is inside, I know that one means it's been moved to the left. So it's pretty easy to see that of the 2 that are left, the only one that's been moved to the left is this one. So you notice what I'm doing is by process of elimination, I am matching them all, and that finally means this one has to be B. So that's the way you go about working one of those matching problems, and you will have one like that. Looking at 5, it says starting each time with the function y equals x cubed. So we go back to starting with this each time. Write the resulting function for each of the following transformations. So starting with the parent function, if you shift it up 4, that's a vertical shift, it would be y equals x cubed and then up 4. Now we go back to starting with this again. Okay, this is different than the one that's following. Shifted to the right 4 means inside the function we have a -4. Remember, this is the one that's counterintuitive. The right is a minus. And then cubed on the outside. Now go back to the parent function and then reflect across the x-axis. To reflect across the x-axis, you substitute -y for y, which means you put the negative out front like that. Not the x in parentheses negative, but the negative out front. Now this next one is different because it's progressive. So we start with the function y equals radical x, and we continually apply the function to see what we end up with. So let's look at how this one's different. First, I want to shift this graph up 2. So it's going to be y equals square root of x and then plus 2. I sort of exaggerated, but make sure it's obvious that the plus 2 is not under the radical sign. Next, we want to take this and we want to reflect it across the x, meaning the whole thing gets the negative applied to it. Now, this is where you have to be careful. The negative is applied to the whole right-hand side. So negative square root of x plus 2, you can leave it like that, or you can distribute it, which would be negative radical x minus 2. Finally, we're going to take this and reflect that across the y-axis. And when we do that, that means that we put in a negative in the x spot. Everything else stays the same. I'm just going to go ahead and write it right here. There's no need to write it twice. So that would give us the negative. I'm going back to what we had here. But where the x is, I put negative x and then minus 2. So negative radical negative x minus 2 is our final function when we did it continuously. We did it repeatedly to what we had prior. All right, looking at the next page, we're still using transformations here, and it says to graph the function using the techniques of shifting, compressing, stretching, and or reflecting. And we start with the graph of the parent function and show each stage. All right, it says do not use your graphing calculator except to check your answer. So here is what we want to end up with. The parent function here is f of x equals square root of x. Okay, so f of x equals square root of x. We have the point 0, 0, 1, 1, and then we have the point 1, 2, 3, 4, 2. So our graph is shaped like that. Now, how did I know those points? Because I actually did a quick XY table. I put in 0 for x, I put in 1 for x, and I got 1, and then I put in a 4 for x, took the square root of it, and got 2. So I know that graph because I've memorized that parent function. Now we're going to do this inside part, and then we'll add the end. So my next one is going to be f of x equals square root of x minus 2 under the function, or inside the function. So what that means is my graph went right to. So what was 0, 0 moves over to here. So I'm basically adding 2 to my x values. So I'm going to write that. So right 2, it's what it affects the x with a plus 2. So 0, 0 becomes 2, 0. 1, 1 becomes 3, 1. 1, 2, 3, 1. 4, 2, add a 2 there, becomes 6, 2. So 1, 2, 3, 4, 5, 6, 1, 2, and it's shaped like that. So we're doing a little more than just the general shape in a sketch. We're actually finding those points. All right, last step is to do that vertical shift on the end. So it's f of x equals square root of x minus 2, which we already did right here, and then we are going to go up 1 with our vertical shift. Now, when you go up, the up 1, what does it affect? It affects the y. From here, we're going to add 1. So the point that was 2, 0 becomes 2, 1. The point that was 3, 1 becomes 3, 2. The point that was 6, 2 becomes 6, 3. So we have 2, 1, we have 1, 2, 3, 2, and we have 6, 3, which is up here. It's the same shape, but it has moved up 1, so it affected my y's. All right, in this next one, this is another matching one. This one's kind of tricky because all of my functions are written in form 2, where everything has already been FOILed out and it's written as a complete function, not in transformation format. So we're going to have to look at this a little differently, and I think the easiest way to do it is to look at it and find on each one of these, find our vertex and look at whether it opens up or down. So as I glance across, I see that this one opens up because it has a positive. This one opens up, this one opens up, this one opens down, up, up, and up. So there's only one that opens down. So that should make it fairly easy as to which one, our one that opens down is this one, and the only one of my equations that open down is B. So that was easy. I'm going to move this up so we have some workspace. So let's just go by our function. On this first one, on A, my A is 1, my B is 0, my C is -1. And I know that the vertex is at -B over 2A. So that's going to be 0 over 2 times 1, or 0. And then I find f of 0, and f of 0 in here would be 0 minus 1. So my vertex here is at 0, -1. So let's find one of our graphs whose vertex is at 0, -1. And if we look, 0, -1, 0, -1 means the vertex is down here, and the only one that is like that is right here. So that is A. So we're approaching this a little differently than we did in the last matching one. We're using the vertex because of the information that we were given. All right, B we already have. We don't need to do it that way because it was the only one that opened down. So let's look at C. C, I have A is 1, B is -2, and C is 1. I'm getting that right here, 1, -2, and 1. So my vertex, -B over 2A, is the opposite of -2 over 2 times 1, or 2 over 2, which is 1. Now I need f of 1, so I'm going to go up here, and I'm going to find f of 1 is 1 squared minus 2 times 1 plus 1, or 1 minus 2 plus 1, which is 0. So now I'm looking for the one whose vertex is at the point 1, 0. So the only one that's at the point 1, 0 is right here, so I know that this one has to be C. I hope you get the idea of what I'm doing. It's a little bit more work than the one when they're given in transformation form. All right, let's look at D. For D, my A is 1, my B is 2, my C is 1. So -B over 2A is -2 over 2, or -1. So the -1, now I need f of -1 in this equation. I'm on D, so I'm on that equation. So it's going to be -1 squared plus 2 times -1 plus 1, or that's equal to 1 minus 2 plus 1, which is also 0. So for that one, I'm looking for the vertex that is at -1, 0. -1, 0, I believe, is right here. So that is my D. All right, let's look at E. X squared minus 2x plus 2. So for E, my A is 1, my B is -2, and my C is +2. So -B over 2A is 2 over 2 times 1, which is again 1. Now I need f of 1 in that equation, which is going to be 1 squared minus 2 times 1 plus 2, or 1 minus 2 plus 2, which is 1. So I'm looking for the one whose vertex is at the point 1, 1, and I believe that one is right here. So this is E. I've only got 3 more, F, G, and H, and I think we're going to need another paper to do those. Let me see if I can find a sheet here. Yes, and we'll move this up here and do those. I don't have space, and then we'll look at our graphs. So we've done E. Now we come to F, and I have A is 1, B is 2, C is 0. So negative B over 2A is negative B over 2 times 1, which is negative 1. I now need F of negative 1, and I'm looking at this equation here. So it's negative 1 squared plus 2 times negative 1, which is 1 minus 2, or negative 1. So I'm now looking for the graph. Let's go back to our graphs for F, whose vertex is at negative 1, negative 1, negative 1, negative 1. This is F. We really only have one more, G, because once we're done, then the one that's left will be H. So for G, my A is 1, my B is negative 2, my C is 0. So negative B over 2A is the opposite of B, it was a negative 2, over 2 times 1, or 1, 2 over 2. Now I need F of 1. In that equation, 1 squared minus 2 is 1 minus 2, negative 1. So I'm looking for the vertex that is at 1, negative 1. Now the only two I have left are these two. Well, this one is at negative 1, 1, but I want the one that's at 1, negative 1. So this one is G, which means the only one that is left has to be H, and you have matched. That was quite a bit of work. All right, looking at our next page, number 9, it says graph the function by starting with the parent function and using transformation. So we're doing a lot of this. Do not use a graphing calculator. Here, my parent function is f of x equals x squared. So I have the point 0, 0, 1, 1, negative 1, 1, and the shape is about like this. Now, the next one is I'm going to put on this 1/4. So it's going to be f of x equals 1/4 times x squared. That is a vertical compression. And what does it affect? You're going to see that it affects our y. It affects our y. It affects the y. Let's do a few points here to do it like we did on the last one. So we have the point 0, 0. We have the point 1, 1 squared is 1. We have the point negative 1 squared is 1. We have the point 2, 4, and we have negative 2 is also 4. So it's going to affect our y because it's going to take my x value once I square it and multiply it by 1/4. So that's going to give us the points 0, 0. Now I'm going to take my x, which is going to be 1, the first x, square it. X is 1, that's still 1, and 1/4 is going to be the y. Take my negative 1, square it, which is 1, multiply it by 1/4. All right, let's continue with 2. Take x is 2, square it, that makes 4, multiply it by 1/4, and I get 1. Take negative 2, square it, multiply it by 1/4, and I get 1. So I have those points, 0, 0. I have 1, and it's just barely up, and negative 1 barely up, just 1/4. And then 2 is at 1, and negative 2 is at 1. So you can see what that vertical compression did was it widened it. Finally, I'm going to add a 1. We know that's a vertical shift. I'm running out of space here, a vertical shift, and we know that it affects the y. So we're going to add a 1 to all of our y's. So that's going to give us the point 0, 1. 1. Now we're adding 1. That's going to make that 5/4. 4/4 plus 1/4. Negative 1 5/4. I'm going to have the point 2, 2, and negative 2, 2. So what's going to happen is it's going to be shaped just like this, but it's going to be up 1. So there you go. All right, let's look at the next one. It says graph the function by starting again with the parent function and using transformations. Do not use a graphing calculator. So here, our parent function again is f of x, or y, equals x squared. We know that that's here, here, here. We can sketch it. The first thing we're going to do is f of x equals x, or let's do 2x squared. It wouldn't have mattered. I could have done either the -1 or the 2. This is a vertical stretch. It's a stretch. It's going to narrow it, affecting the y. It's vertical. And so instead of us having 0, 0, plus or minus 1, 1, and plus or minus 2, 4, what we're going to now have is the y is going to be twice that. So 0, 0, plus or minus 1, and then multiply that by 2, plus or minus 2, multiply that by 2, makes it 8. So what you're going to see is 0, 0, 1 up to 2, negative 1 up to 2, 2 all the way up to 8, negative 2 up to 8. So you can see that what has happened to my function and my graph is, whoops, is it has become narrower. That didn't show up very well. My pen is not wanting to write. There we go. It's becoming narrower. Now we're going to apply this, which is a horizontal shift. We know that affects the x. So it's going to be y equals, we keep our 2, but now it's going to be x minus 1 squared. And we know that moves it to the right. So it's exactly this, except it's moved to the right. I'm not going to go ahead and find the points, but we certainly could. And then our last step is a vertical shift, which takes this and brings it down 1. So that's going to bring it here, and it's still going to be narrow, and we could find some points, and probably we should do that. Here, when I moved it to the right, 0, 0 became 1, 0, because I moved it right 1, so the x was affected. It became 2, 2. It became 0, 2. It became negative 1, 8, and 3, 8. Those are the points. If I continue with those points, my 1, 0 becomes 1, negative 1. Then I have the point 2, 1. So instead of 2, 2, it's 2, 1. And then I have, instead of 0, 2, I have 0, 1, because it brought it down 1, etc. Instead of 3, 8, I have 3, 7. I should have had those in reverse, by the way. Instead of negative 1, 8, I have negative 1, 7. So you could plot those points. It's important to know what the shifting does, what it affects, the x or the y. Now we're going to work with the second form, form 2, where our function is not in transformation format, but it's already been all multiplied out. So here is our function. We know that it opens up, and how do we know that? Because our a is positive. It's a positive 1. Our b is 2. Our c is negative 8. But it's because our a is greater than 0. I know that it opens up. The vertex is negative b over 2a, which is negative 2 over 2, which is negative 1. That's the first part of it. Now I have to find f of negative 1 in this function. Negative 1 squared plus 2 times negative 1 minus 8, or 1 minus 2 minus 8, which is negative 9. So my vertex is at the point negative 1, negative 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's clear down there. We know it opens up, but we don't know how it's shaped yet. The axis of symmetry, once you have your vertex, you have your axis of symmetry because it's just the line x equals the x value. So it's the line that goes through x is negative 1. The y-intercepts are when x is 0, and that's easy. So we want f of 0, which is 0 squared plus 2 times 0 minus 8, or just the point 0, -8. So it's going to cross my y-axis right there, which means I also have this point because of that axis of symmetry. My x-intercepts are when y is 0, so I take this and I set it equal to 0. That is factorable. It's going to be x plus 4, x minus 2 equals 0. Using the 0 factor property, you're going to get that x equals -4 or +2. So my 2 points are -4, 0, my 2 x-intercepts, and the point 2, 0. So it's going to cross here and at -1, 2, 3, 4. Now I can sketch it. It goes up through here like this. It goes down to the vertex and up through there like that. And that is the shape of it. The domain is how far it goes left and right. I'm kind of out of space, so I'm going to put this down here. The domain is -infinity to infinity, but the range, it does have a low point. That low point is when y is -9, but it goes up all the way to infinity. You can see that it is decreasing from x being -infinity down to x is -1, and then it changes right there. It starts increasing when x is -1, and it increases up to x being infinity. So that's how you analyze it, a function when you are given it in the other format. All right, continuing with number 12, it says determine without using a graphing calculator whether the given quadratic function has a max value or a min value, and then find the value. Well, we know if it has a max or a min, that has to do with where the vertex is. So let's go ahead and list our A, B, and C. A is positive, it's a 2. B is a +12, C is a -3. Since the A is positive, I know that it opens up, so I already know that it has a min value, not a max value. Now we want to know what that is, so we're going to do again -b over 2a, or -12 over 2 times 2, -12 over 4 is -3, that's the first part, and now we want f of -3, so f of -3 is going to be equal to 2, take out the x, put in the -3, plus 12 times -3 minus 3, this is 9 times 2 is 18, minus 36 minus 3, which is -21. So I know that it is a vertex right here at -3, -21. It is a min value and it's opening up. And that's all you needed to figure out for that one. The next one is an application problem. It says, suppose that the manufacturer of a gas clothes dryer has found that when the unit price is $P, the revenue is this equation. R of P equals -4P squared plus 4,000 P. What unit price should be established for the dryer to maximize revenue? And what is the revenue, the maximum revenue? So using this equation right here, I know that my A is -4, my B is 4,000, and my C is 0. So if I want it to be maximized, I know that that's a max point that looks like that, and I know it's the vertex. So again, we need -b over 2a, so that's going to be -4,000 over 2 times -4, or -4,000 over -8, which is 500. So that's the first thing that we needed. What unit price should be established for the dryer to maximize revenue? $500. And then when you charge that much, what is the maximum revenue? That means what is F of 500? So we're going to put that into our equation. It's just a calculator problem. 500 squared, I'm putting it in right here for the P in the equation, plus 4,000 times 500. You can use your calculator and put that in. Be careful here. You square the 500 first and then you multiply by -4. And you end up with this, $1 million. So that means at $500 each, the revenue will be maximized at 1 million. I can show it as a point, 500 and then 1 million. I don't want to put the commas in because it gets confusing there. That's the point, the vertex point. But this is the maximum revenue, and this is the unit price that causes the revenue to be maximized. All right, the next one says the price in dollars and the quantity X sold of a certain product obeys the demand equation, where P is for price and X is the quantity sold. Express the revenue as a function of X. So what we want is R of X, and it's always going to be, I'm going to write this up here, the revenue is equal to the number you sold times how much you sold them for. So it's going to be X times P, but P is equal to this. So X times -1/6 X plus 100. Now we need to clean that up a little bit, which is -1/6 X squared plus 100X. That is R of X. That's all they were asking for right there. What is the revenue if 200 units are sold? We're just going to put a 200 in for X. It's just a calculator problem. So we want R of 200, -1/6 times 200 squared plus 100 times 200. Put all that in your calculator, and what you're going to get is $13,333.33 if you put that in the calculator. So with this equation, if you sell 200 units, this is what you will make. What quantity maximizes the revenue? So from this equation right here, we want to know our A, B, and C. So our A here is -1/6. Our B is 100, and our C is 0. So -B over 2A is equal to -100 over 2 times -1/6, or -100 over -1/3. I can cross cancel fractions, equals 300. So that's the quantity that maximizes the revenue. So that's the first part of our vertex. Now we want to know, what will you get if you produce that many? So we want F of that, or R of 300 back in our equation. So it's -1/6. I'm using this equation right here. Take out that X, put in 300 squared plus 100 times 300. Calculator problem. R of 300 is equal to 15,000. So when you sell 300, you will make your maximum revenue of 15,000. What price should they charge to maximize the revenue? Well, what we want to know is, if you go back to the equation, here's our X, this is our X, this is R of X, so I want to put my 300 back into that equation. So P equals -1/6 times 300 plus 100. This actually cross cancels. P equals $50. So that's how much they should charge. One last maximizing problem. This is an important one. It's a little different than the ones that we did in our notes in class. Maximizing area. It says a farmer with 4,000 meters of fencing wants to enclose a rectangular plot that borders on a river. If the farmer does not fence the side along the river, what is the largest area that can be enclosed? So he has this perimeter amount, 4,000. So rather than X, I'm going to cross these out, and we're going to use width and length. But notice the perimeter in this case the perimeter is made up of 2 widths but 1 length. Only 1 length. So if I want to solve that for the length is going to be equal to P minus 2W. But I know what P is, it's 4,000. So the length is equal to 4,000 minus 2 widths, because we're not using two lengths. So this is equal to 4,000 minus 2 widths. I also know that area of any rectangle is length times width. So area, if I only want to use widths, okay, it's going to be this length, 4,000 minus 2W, times W. Now I have area as a function of W. Now we're going to distribute. So area as a function of W equals 4,000 W minus 2W squared. Let's rearrange that to be traditional. Minus 2W squared plus 4,000 W. Now, we want to maximize that area. That's the vertex again. So our A is -2, our B is 4,000, our C is 0. So the vertex -B over 2A is -4,000 over 2 times -2, which is -4,000 over -4, which is 1,000. That's the width that we want. That's the width that we just found. So now we need to do 2 things. We need to find the length. That's going to be 4,000 minus 2 of the widths, or 4,000 minus 2,000. The length is going to be 2,000. So it'll be 2,000, 3,000, 4,000. It adds up to our 4,000. Now to find the area, you can either multiply length times width, which would be 2,000 times 1,000, or you can find A of 1,000 in our formula. It's going to come out exactly the same. I actually think it's easier to do it this way. But A of 1,000 in that formula would be -2 times 1,000 squared plus 4,000 times 1,000. I ran out of space. Either way, you're going to get A of 1,000 is equal to 2 million square meters. So once you have found your width that maximizes the area, you can just go back here and find your length and then find area this way rather than doing it this way. Same thing. There's one last problem from section 3.3, so it's out of sequence here, that I added to the end of this test review because I wanted to do one of these one more time. We did these when this kind of problem when we actually did the topic in the guided notes, but on your test review I want to do one more. So it says the graph of a function f is shown here, labeled with 4 points. Use the graph of x to sketch the graphs of each of the following functions. Label 4 points on each of the graph. And the way that I showed you to do this, let me move it up a little bit, is to write the point that we start with, and then we're going to write what it becomes. You probably remember this from the topic notes. So let's try this first one by writing down the points that we have. We have -4, -2. We have the point 1, 0. By the way, I'm just getting these right from here, from my original graph. We have the point 2, -3, and we have the point 3, -3. And what we want to know is what each of those becomes as we go through each of these transformations. So let's look at the first transformation. This 2 in front of the whole thing is a vertical stretch. It makes the shape skinnier, which is going to be hard to recognize on this a little bit, but all you have to know is, does it affect the x or the y? It affects the y because it's in front of the whole thing. It wasn't done to just the x inside. It affects the whole thing, so that is the y. So what we're going to do is take each of our y's and multiply it by 2. That's all you're doing. So y becomes 2y. So the x stays the same, -4, multiply by 2, -4. 1 stays the same, multiply the 0 by 2, and you still get 0. 2 -3 becomes 2 -6, and 3 -3 becomes 3 -6. Now all we have to do is plot those points and connect the shape. So we have -4, oops, wrong place, -1, 2, 3, 4, and then down 1, 2, 3, 4. Let me see if I can get this. It's about right here. It's hard to do this level without the grids like you guys have. Then I have the point 1, 0, which is right here. So this, oops, I missed a little bit, represents this part. It's steeper. That's the stretching. And then I have the point 2, -6. So I've got 2, -1, 2, 3, 4, 5, 6 is about right there. And then I have 3 -6's right next door to it. So these two are going to be connected, and this goes down like that. And again, as I told you in the topic notes, I would rather you show it like this than label it on here. It's not necessary because it gets kind of small. So it's fine if you have point and becomes. So remember that when you are tested. All right, let's look at the second one. We're going to start with the same points. So my point, and then what it becomes. So we have -4, -2. Remember, we go back to the start. Then we have 1, 0. I have 2, -3, and I have 3, -3. And we're going to write what those become when you do this. This represents a horizontal shift. It is to the left, so it affects the x. So x becomes x minus 2. All right, so the x is what's affected. The y's stay the same. So -4 subtract 2 becomes -6. Y is the same. 1 subtract 2 is -1. The 0 stays the same. 2 subtract 2 is 0, -3. 3 subtract 2 is 1, -3. So that was pretty simple. -6, -2, -1, 2, 3, 4, 5, 6. -2 is about right here. And then -1, 0 is right here. 0, -3, 1, 2, 3 is right here, and 1, -3 is right here. Now we just connect. It's the same shape that you started with, but it was shifted to the left too. So that's why you have this point becomes this point. All right, let's do the last one. Let me scoot this over so you've got plenty of space to see. We're going to list our point again, and then we're going to list what that point becomes. So we, again, -4, -2, 1, 0, 2, -3, and 3, -3. So let's look at what we're doing. Out front, that negative works just like that 2 did out front. Not a vertical stretch, but it is done to the y. What is that? That is a reflection across the x. So it affects the y. Y becomes -y. And those little notes will help you know what to do. So the x's are going to stay the same. So -4, -2 becomes -4, +2. 1, 0 is 1, 0 because it doesn't, the y, -y doesn't change that. 2, -3 becomes 2, +3. 3, -3 becomes 3, +3. Plot those points. -1, 2, 3, 4. 1, 2 is right here. 1, 0 is right here. 2, 3 is 2. 1, 2, 3 right there. And then 3, 3 is right beside it. And you can see it is this shape, but flipped around that x-axis.